Hello students, myself Kishore and Gujjar, Assistant Professor, Department of Physics. Today we will discuss about I-section girders and some of the problems in this chapter. When heavy beam or girder is supported at its end, it's bent under its own weight. The depression at its center is given by y is equal to mgl cube by 4y bd cube. So here y is the depression produced by the beam, L is the length of the beam, y is the Young's modulus of the material, b is the breadth of the beam or girder, d is the thickness of the girder. In this expression, y is directly proportional to L cube, y is inversely proportional to Young's modulus, y is inversely proportional to breadth, and y is inversely proportional to thickness. It means that as the length of the beam or girder increases, the depression in the beam is also increases. If there is a decrease in Young's modulus of the material, that increases the depression in the beam. In the same way, if you decreases the breadth or the thickness of the material, that increases the depression of the beam and vice versa. So, due to the depression, the upper part of the beam above the neutral surface contract while those below expand. Hence, the stress is maximum on the lower or upper surface of the girders. Therefore, the upper and the lower surface of the beam must be stronger than its intervening part. The surface of the girders or iron rails are made much broader than the rest of it, which gives the cross-sectional shape of the letter I. Hence, it is called as a high section girders. In this matter, we can save the material without appreciably imparting its strength. So, here this can be seen in the railway track, also in the construction of building. So here we use the I section girder to save the material without changes appreciably its strength. Next, we will move on to some of the problems. So here the first problem is find the work done in stretching a wire of 1 square millimeter cross section and 2 meter long through 0.1 millimeter. So here the given is the Young's modulus is equal to 2 into 10 to the power 11 Newton per meter square. So we know that in order to calculate in a work done in a stretching wire is equal to half into stretching force into stretch. So in this problem, the given data are y is equal to, that is Young's modulus is equal to 2 into 10 to the power 11 Newton per meter square. Here the original length of the wire is L is equal to 2 meters. Okay, when you apply the force, it increases an amount that is equal to small l, that is equal to 0.1 millimeter. So that can be written as 10 to the power minus 4 meter, and area of cross section of that wire y is equal to 1 square millimeter, that is equal to 10 to the power minus 6 meter square. So here from the formula we know that work done in a stretching a wire is equal to 1 by 2 into stretching force into stretch. But we know that from the definition of the Young's modulus is equal to FL by AL, or F is equal to YAL by L. Substitute the value of F in this equation, then this equation becomes 1 by 2 into YAL by L into L. So here the Young's modulus, that is 2 into 10 to the power 11 Newton per meter square. The area of cross section is nothing but 10 to the power minus 6. The L, that is the change in length or increase in length, that is 0.1 millimeter or 10 to the power minus 4 by L, it is a original length, that is 2 meters, and into L, that is 0, that is 10 to the power minus 4 meter. When you substitute this value, finally here we can get the work done is equal to 5 into 10 to the power minus 4 joule. The next problem is the calculate the twisting couple on a solid shaft of length 1.5 meters and diameter 120 millimeter when it is twisted through an angle 0.6 degree. The coefficient of rigidity for the material of the shaft may be taken to be 93 into 10 to the power 9 Newton per meter square. So here in this problem, the length of the cylinder is given, or the solid shaft is given, that is L is equal to 1.5 meter, and its diameter is 120 millimeter, or it can be written as 0.12 meter. So therefore the radius it's become 0.06 meter because r is equal to d by 2, and the coefficient of rigidity modulus is neta is equal to 93 into 10 to the power 9 Newton per meter square. We know that the couple per unit twist is given by pi neta r to the power 4 by 2L into theta. When we substitute the value of pi, so that is 3.14, neta is 93 into 10 to the power 9, r is 0.06 divided by 2 into L, then here we can get the C is equal to 1.322 into 10 to the power 4 Newton. So in the third problem, a brass bar 1 centimeter square in cross section is supported on two knife edges 100 centimeter apart. A load of 1 kg at the center of the bar depresses that point by 2.51 millimeter. What is the Young's modulus for brass? So here in this problem, the data some of the data is given, that are, that is B, that is equal to 1 centimeter. The length of the bar, that is equal to L is equal to 100 centimeter. The mass of the bar is given, that is M is equal to 1 kg, and here the depression produced by the bar is given, that is Y is equal to 2.51 millimeter. So when the weight is supported at its end and it is a depression produced at the middle is given by Y is equal to 4 mg L cube by YB D cube. So here M is the mass, G is the acceleration due to gravity, L, that is equal to 100 centimeter is given. Here the Y is the Young's modulus, B is the breadth, and D is the thickness. When you substitute this value, here we can get the Young's modulus of the material is, that is 9.79 dynes per centimeter. So in the next problem, the modulus of rigidity and Poisson's ratio of the material of the wire are 2.87 into 10 to the power 10 Newton per meter square and 0.379 respectively. Find the value of Young's modulus of the material of the wire. So here in this problem, we are given the value of rigidity modulus, that is the neta 2.87 into 10 to the power 10 Newton per meter square, and the value of the Poisson's ratio, that is sigma, is equal to 0.379. The relation between the Young's modulus, the rigidity modulus, and the Poisson's ratio is given by the Y is equal to 2 neta into 1 plus sigma. Here we know the value of neta and sigma. Substitute the value of neta and sigma. So here we can get the Young's modulus of the given material. Thank you.